The connection of the distributed generation can impact voltage and current unbalance in a number of ways. Large phase units are many randomly distributed small units with which will result in increase in unbalance. Single phase generators unit not only expected that in a low voltage network, most likely a domestic and small commercial customers are also. The connection of a three-phase generator will limit the voltage unbalance either by creating the low impedance path for a negative sequence impedance or by creating unbalanced voltage source. At transmission and sub-transmission level, shift from conventional generators to distributed generation could result in increase in unbalance. Moving on, let us see a weak transmission system. When more distributed generation is producing power, less large conventional generator unit will be in operating. The result is that short circuit capacity in transmission and sub-transmission level. The same unbalanced current will give more unbalanced voltage. The two main sources of unbalanced voltage are transmission level are as follows. Unbalanced non-transpose or not well transpose transmission line generate a negative sequence voltage even with only a positive sequence current that is flowing through a line. For a transmission line, especially when not transposed, a negative sequence voltage is up to 2%. Large single phase loads such as arc furnace and railway traction takes heavily unbalanced current. High speed railways are reported to be a main source of unbalance in some countries. The former contribution is less affected by the amount of conventional generators that are connected to the system. The latter contribution is inversely proportional to the fault level. So when the fault level halves, the voltage unbalance doubles. A significant increase in unbalance is expected at a transmission level when conventional power stations are close to a large single phase load that are in operation only for a part of time or not at all. So it is very difficult to predict beforehand for which amount of distribution will take place. It should be also noted that the consumption also shows a variation, so that amount of generation connected to the transmission grid will change with time anyway. So next to that, opening up of electricity market will result in the power transfer over longer distance. All these will result in the temporary or local weakening of transmission grid. The shift from large power station to the distributed generation will further contribute to this, but it is not only a cause. The actual impact will strongly depend on the way in which the connection of large installation with unbalanced current is assessed. So in the IEC technical report for the connection of unbalanced installation, it is recommended to use the lowest fault level, so that could occur during in normal operation. With large penetration of generation not contributing to the fault level, the lowest fault level to be considered corresponding to the maximum consumption, coinciding with the maximum production. So this could locally result in the significant reduction in the fault level. So maintaining the same plan level for unbalance could make the connection installation much more expensive. So this is about the weaker transmission grid. So let us see the stronger distribution system. The presence of three-phase generator which are connected to the distribution system gives a decrease in the negative sequence voltage. The negative sequence impedance of a induction machine and a synchronous machine is less than zero 0.2 per unit. When a generator transformer is used, its impedance should be added to the negative sequence impedance. The reduction in the unbalance becomes less in that case. Distributed generators connected to the power electronics interface will also improve the unbalance locally. It is seen from the grid, the generator can be represented as a positive sequence voltage source behind the reactance. For negative sequence, it is only this reactance that matter. The small impedance, the more generator unit reduces to negative sequence voltage. So this comes, however, at an expense of larger negative sequence current that is flowing through the converter. Typically, the value of the reactance used in the power electronic converter are between 0.1 and 0.2 per unit. That is in similar range as a negative sequence impedance of induction and synchronous machine. Again, the use of generator transformer will increases that negative sequence impedance and thus reduce the ability of a distributed generator to the reduced voltage unbalance. So all these are some of the effect with the strong distribution system. So now let us look for the large single phase generators. The connection of large single phase generator will result in the injection of positive and negative and sometimes zero sequence current at same amount. The production of active power, that is P-gen, and zero reactive power current is equals to I is equals to P-gen divided by U, where U is the phase to neutral voltage at a point of connection. So it has been assumed here that generator that is connected to phase to neutral, the negative sequence current that is injected by single phase to generator is equals to I2, that is 1 by 3 times of I, which is equals to 1 by 3 times of P-gen by U. So this equation can be rewritten as P-gen divided by 3U. So negative sequence current will also result in negative sequence voltage. The ratio between the voltage and current being determined by negative sequence impedance Z2 at a point of connection, where U2 is equals to I2 into Z2, that is P-gen divided by Z2 divided by 3U. Here the negative sequence impedance Z2 is in parallel connection of series impedance of a grid and the shunt impedance due to local load. Z2 is in parallel connection with the series impedance of grid and shunt impedance due to local load. So this is shown mathematically. The series impedance ZS2 is mainly the impedance of distribution transformer and varies between distribution transformer and a point of connection. The shunt impedance ZL2 is mainly determined by negative sequence impedance of the load in the neighborhood of a point of connection. Three-phase motors with their low negative sequence impedance will dominate this impedance. So this is with respect to a large single phase generator. Here we have seen a current that is zero reactive power gives the current which is equals to I is equals to P-gen, and also we have seen negative sequence current that is injected to the single phase generator. So with this we move on to mini single phase generator. This is a large single phase generator. Likewise we will see many single phase generator. The presence of a large number of single phase generator, that is up to few kilowatt, will result in the increase of unbalanced voltage network. Examples are this domestic CHP and rooftop solar panel. When multiple single phase generator unit connected to the same feeder, they will most likely to be randomly distributed over the three phase. The probability that they all are connected to the same phase will decrease quickly with the increase in the number of generators. For n unit, the probability that they are all in same phase, which is equals to PR n is equals to n divided by 1 by 3 power n minus 1. So here there are different graphs produced for the probability as a distribution function for the number of generator unit in one specific phase. We will see that for a total 6 unit and 30 unit. So these are the graphs that are representing the probability distribution function for the number of generator units in one specific phase. One is for the A is for 6 unit and B is for 30 units. Okay. Since he is mentioned 20, it is of 20 unit, not 30 unit. So he is wrongly mentioned. It is 20 units. Okay. So the probability that they are all in specific phase. For example, in a phase A, 1/3 of this, that is 1 by 3 n for 3 units, the probability that they all are in same phase, so which is equals to 11%. For 6 units, the probability is only 0.4%. For 9 unit, the probability is small as 0.015%. With a large number of small single phase generator, there is thus an obvious no need to design the network for an situation that all the units are connected to the same phase. The units will, however, in most cases, will not spread equally over the three phases. So some unbalance may remain. We will estimate this unbalance. Spread of generators over a phase is illustrated in our one more diagram that I will show in our coming slide. A Monte Carlo simulations has been done to estimate the probability that a specific phase would contain certain number of generator unit. So I am talking with respect to this. These calculations have been performed when the total 6 units are connected to the feeder. When a total of 30 units are connected to the feeder. In both the cases, 100,000 simulations were performed to obtain the estimate of probabilities. For a 6 generator, the number of units connected to the one phase varies with 95%. That is confidence between 0 and 4. For 30 unit, it is varying between 5 and 15. With increase in the number of single phase generator unit, the negative sequence current increases. Note that the current unbalance decreases with increasing the number of unit. What matters to the grid is absolute value of negative sequence current, as this is determined the negative sequence voltage. Using the above mentioned Monte Carlo simulation, the probability distribution function of negative sequence current has been calculated. From this distribution, the average value and the standard deviation, and it is 95 percentile.